Hello, you are listening to Pankaj Rai, and in this video we will be discussing the numericals of the chapter Atoms, Molecules and Nucleus. So let us begin. We will be discussing the series of spectral lines of hydrogen atom. Now, let us consider a hydrogen atom, okay, and it is having, let's say, one electron in its first shell. Now imagine that there is a photon which is being incident on this electron. The photon is having a frequency of nu, so its energy would be h nu, where h is the Planck's constant. The moment this photon will collide with this electron, it will transfer the complete energy to the electron, and by receiving that energy the electron will move to a higher orbit. Let's say that the electron is moving to this higher orbit. Okay, let's say this is the first orbit and let's say this is the second orbit. So electron has been moved to the higher second orbit on receiving the energy. But this is not the stable state of the electron, so it will after some time again come back to its original orbit, which is the first orbit, and while doing so it will release the amount of energy it has gained in the previous case. So that energy will be released again in the form of a photon, and the energy would be same, E is equal to h nu. As you can infer that this energy of the photon is actually equal to the energy difference between the level of orbit 1 and orbit 2. So when the electron receives an energy equal to the energy difference between the orbits, it moves to that orbit, and while coming back to its original orbit it emits the photon which is equal, whose energy is equal to the energy difference between the two orbits. And it is too obvious that if a higher energy photon will come, then the electron will move to a orbit which will be higher, let's say the third orbit, and while coming back to it, it will again emit or release the same photon whose energy will be higher than that in the previous case, from 1 to 2 and 2 to 1. So it is very simple that when gap or the transition is higher, so similarly the energy would be higher, and because the energy gap would be higher, the photon released would be of a higher frequency, and if the photon is released would be of higher frequency, then obviously the wavelength of that photon will be lesser. So this is a simple relation between the gaps of the orbits and energy of the photon and the frequency of the photon and the wavelength of the photon. And conversely, we can also say that if the gap is less, then the energy difference between those two gaps will also be lesser. So similarly, if E is equal to h nu, the frequency will be less and the wavelength of the emitted photon will be higher. Now we have a relation between the wavelength of the photon released and the orbit number between which the transition is happening, and it is given by 1 by lambda is equal to r times 1 by p square minus 1 by n square, where p is the inner orbit number to which the electron is coming back, and n is the higher orbit number or the outer orbit number, let's say outer orbit number, from which the electron is coming. Now there are 5 series which are defined for the transition of electron from a higher orbit to a lower orbit in hydrogen atom, and let us discuss them. The first series is called as the Lyman series. Now what is the Lyman series? Lyman series occurs due to the transition of electrons from different outer orbits to the first orbit. So if the electron is coming from second to first, third to first, fourth to first, fifth to first, so that series of wavelengths of the photon which will be released is called as Lyman series. Second series is called as Balmer series, and Balmer series arises due to the transition of electrons from outer orbit to the second orbit. Next is Paschen series. It arises due to the transition of electrons from higher orbits to the third orbit. Next is Brackett series, and Brackett series arises due to the transition of electrons from higher orbit to the fourth orbit, and if the transition of electron is happening from the higher orbit to the fifth orbit, then the series of wavelength of the photon which are emitted is called as Pfund series. So I can simply say that these numbers 1, 2, 3, 4, 5 are nothing but the P, which is the inner orbit number, and these are the corresponding series. Okay, now let us move ahead. Let me give you an example that let's say electron is moving from higher orbit 6 to a lower orbit 3. So the wavelength which would be emitted would lie in the Paschen series. And how do we calculate the value of that wavelength? It is very simple. We have to substitute the values in this equation, which is 1 by r, 1 by lambda is equal to r, which is Rydberg's constant, whose value is 1.097 into 10 raised to 7 meter inverse, and then we have to substitute 1 by p square, which is 1 by 3 square, minus 1 by the higher orbit, which is 1 by 6 square. Now you can solve this. It would be 1 by 9 minus 1 by 36. That will be cross multiplication, and in that case you will receive the value of the lambda. So this is one of the example of the questions which are asked. They ask you that if there is a transition from nth orbit to the pth orbit, then find the wavelength of the photon which is emitted. Now the type of questions which I want to discuss are where they ask you to find the shortest wavelength of a series, or to find the longest wavelength of a series. For example, they may ask you find the longest wavelength in Paschen series. That's all they give you. Now what is the meaning of that? Now let us concentrate. For that we have to focus here. Now if you remember that if the gap is larger, that is transition is from a very higher orbit to a very lower orbit, then the wavelength will be less. And if the gap is very small, then the wavelength will be greatest or the longest. Now you could simply imagine, let's say I have to explain you what are the shortest and the longest wavelength of Lyman series. Okay, so let us discuss that. Now what do we mean by the shortest wavelength, and what do we mean by the longest wavelength? Now we want a shortest wavelength, let's say of the Lyman series. Now Lyman series is when the electron jumps from a higher orbit to the first orbit. Now we want the wavelength to be shortest. If we want the wavelength to be shortest, then the gap should be maximum, and the maximum gap will occur when the transition is from, let's say, infinite orbit to the first orbit. So for shortest wavelength of Lyman, the gap should be largest, and for gap should be largest, the electron must be coming from, let's say, an infinite orbit to the first orbit. So in that case the shortest wavelength of Lyman would be given by 1 by lambda is equal to 1 by, sorry, it will be r into 1 by p square. So p is the inner orbit of Lyman series, which is 1 square, minus 1 by the largest orbit from which it is coming, let's say infinite orbit, so it would be infinity square. So shortest wavelength of Lyman is given by this formula. Now 1 by infinity, 1 by infinity or 1 by infinity square is 0, so this term will vanish. So it will be 1 by lambda is equal to r times 1 by 1 square minus 0. Now 1 by 1 square is also 1, so simply we will get that 1 by lambda is equal to r. So this is the shortest wavelength of the Lyman series. It is given by 1 by lambda is equal to r, or lambda, the shortest wavelength of Lyman series, is equal to 1 by r. You substitute the value of r and you get the value of shortest wavelength of Lyman series. Now let us move ahead. Let's say we have to find what is the shortest wavelength of the Balmer series. For Balmer series, the transition should be to the second orbit. For shortest wavelength, the gap should be the largest. For gap should be the largest, the higher orbit should be infinite. So higher orbit will remain same, but the lower orbit or the inner orbit will be changed in case of the Balmer series, and in case of Balmer series the inner orbit is actually the second orbit, so it will be 1 by 2 square minus 1 by infinity square. So it will be 1 by 2 square minus 0, so 1 by lambda will be r by 4, as simple as that. So the shortest wavelength of Balmer series is given by equation that 1 by lambda is equal to r by 4. Now I can continue the discussion similarly, and we can obtain the Paschen series, the shortest wavelength of Paschen series, as 1 by lambda is equal to 1 by, it would be 1 by 3 square. So 1 by 3 square, so it will be r by 9. For bracket, it would be 1 by lambda is equal to r by 1 by 4 square, so it will be 1 by 4 square, which is 16, and you can simply guess that 1 by lambda for phone will be r by 25. So this completes the shortest wavelength of corresponding series. So if they ask you find the shortest wavelength of bracket, you simply have to use this formula that 1 by lambda is equal to r by 16. Substitute the value of r and you are done. Now let us move ahead with the longest series. So let me first erase this part. Okay, so what about the longest wavelength? Let us discuss the longest wavelength of Lyman series. Now, for wavelength to be longest, the gap should be smallest. Now, in a Lyman series, the inner orbit is 1, that is for sure, and for the gap should be shortest, the next orbit or the higher orbit has to be 2 compulsorily, then and only then the gap would be smallest. So, if gap is smallest, let's say electron is coming from second to first, so it will be called as Lyman series because it is coming to first, and since there is only a single transition of orbit second to first, which is smallest, 3 to 1 will be higher, 4 to 1 will be higher. For Lyman we have to have inner orbit as 1, so shortest gap would be 2 to 1 for Lyman. If the gap is shortest, then the wavelength would be longest. So let us use the formula that 1 by lambda is equal to r times 1 by p square. For Lyman series the p is 1, so it is 1 by 1 square minus 1 by n square. Now n for longest wavelength has to be the immediate next orbit, which is 2, so it is 1 by 1 square minus 1 by 2 square, which would be r times 1 by 1 minus 1 by 4. So there will be a cross multiplication, 4 minus 1 by 4, so it will be r times 4 minus 1 by 4, so it would be 3 by 4. So longest wavelength of Lyman is given by a relation which is 1 by lambda is equal to 3r by 4. Now let us go ahead with the longest wavelength of Balmer. Now for Balmer the inner orbit has to be 2, so let me remove this, and in case of Balmer we should have the inner orbit as 2, so it will be 1 by 2 square. The outer orbit for longest wavelength longest, gap should be smallest, inner orbit is 2, so gap would be smallest when there is a transition from the next orbit to 2, that is 3 to 2. So next orbit, the higher orbit has to be 3. So in case of longest wavelength of Balmer series, since it is a Balmer series, the inner orbit has to be 2, and for longest wavelength the higher orbit has to be the immediate next orbit, which is 3. So we have to calculate this. So it would be 1 by 4 minus 1 by 9. It would be 9 minus 4 by 36. 9 minus 4 is 5. So we are getting a relation of longest wavelength of Balmer series as 1 by lambda is equal to 5R by 36. So in a similar way you can calculate the Paschen would be from, as in case the Balmer is from 3 to 2, so Paschen will be from 4 to 3, the bracket is will be from 5 to 4, and the Fun will be from 6 to 5. And you can calculate and fill this table by yourself, but there is a very easy way to remember these values. See, there is a very simple trick here. As you can see, now see, the Lyman is from 2 to 1. Okay, so add 2 and 1, so you get 3. Multiply 2 and 1, so you get 2, and square of that would be 4. Similarly, Balmer is when the electron is going from 3 to 2, add 3 and 2, it is 5. Multiply 3 and 2, it is 6. The square of 6 is 36. So let us derive this. Paschen is 4 to 3, so add 4 and 3, it would be 7R. Multiply 4 and 3, it will be 12. The square of that, 144. So that is the relation of longest wavelength of Paschen. Let us try to find brackets longest wavelength. It will be given by, bracket is when the electron is coming from 5 to 4, so add 5 and 4, it is 9. So 9R upon multiply 5 and 4, that would be 20, and square of that would be 400. And 1 by lambda for longest wavelength of Fun. Fun is from the electron is moving from 6th orbit to the 5th orbit, so add 6 and 5. 6 plus 5 would be 11, so it is 11R upon 6 into 5 is 30, and the square of 30 is 900. So in this way you can get the shortest and the longest wavelengths of corresponding series. Now the type of questions asked on this topic depends on this. They may give you the higher and the lower orbit and ask you to find the corresponding wavelength, or they may simply ask you to find the shortest wavelength of Paschen or longest wavelength of Fun. Or there is one more type in which what they do, that they give you that longest wavelength of Fun is given to you, and they may ask you the shortest wavelength of Balmer. So what you have to do, the longest wavelength of Fun is given, so you have to use this equation. And let's say they are asking you shortest wavelength of Balmer, so you have to use this equation. Now longest wavelength of Fun is given, so they have given you the lambda, okay, and you have to find the shortest wavelength of Balmer, that is you have to find this wavelength, this lambda. So simply you have to take this equation and this equation, and you have to divide them, and when you divide them the R will get cancelled, okay, and there will be only numbers with the wavelength of Fun which is given to you, so you will simply get the wavelength of the Balmer. So these are the simple numericals on the series of spectral lines of hydrogen atom. Thank you very much.